It is a real pleasure to have with us today Judith Lean. I think it's very hard to present yourself because you have served on so many committees and been on so many different places. If I had to summarize, I can look at your CV, but she has, well, you have testified to the US Congress, so you're part of the same team as James Thompson and all the others.
Hardly.
And so Judith has been very productive in everything that relates solar variability and climate change, also playing a major role in the IPCC report a couple of years ago. And she's also behind this NRSSI model, which many people are using to use solar forcing for climate models. And she has received a bunch of awards, and I cannot name all of them because there are just too many. And she's an American Geophysical Union Fellow, US National Academy of Sciences member, an American Philosophical Society member, just to name a few. So again, I think it is really a pleasure for us to have you with us, Judith. For those of you who are not familiar with these webinars, we have them now on a monthly basis, and we change topics, so the next one can be on something completely different. The webinar will be recorded, so you can still listen to it and come back to if you have missed something. If you have questions, please write them down in the chat, because after the presentation, we will go through them, time permitting. And so if you do have questions, don't hesitate. With that, I think we're ready to start. I'm Thierry de Levet, so I'm happy to host this webinar today at EC. And Judith, I'll let you start.
Okay, thank you, Terry. It's lovely to be here. Hello, everyone. Happy to talk to you wherever you are. So the title of my talk, Big Picture, Sun, Climate and Ozone. And by the way, can everyone hear me? Is everything working properly?
Yeah, it's fine. Yeah.
Okay, good. So when I started thinking about this, it occurred to me that the whole issue of ozone change and climate change has basically informed my whole career. The problem's been around for a long time, more than 40 years. And the sun has had a sort of somewhat dubious role in all of this, because we need to know what it does do, but also what it doesn't do. So I'm going to sort of go through where I think we are now in understanding this whole connected system of how the sun creates ozone, establishes the climate, and how all of these things are varying. So everyone knows that incoming solar radiation heats the Earth. If we didn't have the sun, I like to say, we wouldn't have a greenhouse effect. It establishes the Earth's climate. It also creates the ozone layer, because ultraviolet radiation destroys oxygen, and then that recombines to ozone. As I said, ever since I've been working, like basically since I was aware of geophysics, anthropogenic gases have been an issue, understanding what they do. They trap outgoing terrestrial radiation that further heats the Earth, and also different sorts of gases destroy ozone. So I'm going to actually go through in the first few slides a sort of concept of this system and what we need to know about it. The detection and attribution and forecasting of climate change and ozone depletion and recovery by whatever means, like from all both natural and anthropogenic influences, basically, as I said, has motivated earth science research for the past 40 years, and I expect for the future as well. Okay, so it's not moving. Got it. Okay, so this is a picture of the sun and the Earth in space. The sun has its own energy source. It's a black body that radiates at about 57-70 K, and it emits radiation in the form of the spectrum shown here in the bottom panel, peaks in the visible radiation. The heat comes from the convections from the core, which then radiates through the radiative zone to the convection zone. It causes things to erupt on the surface, like sunspots, and this alters the amount of photons that reach the Earth. The Earth has, it's also a black body in space, and it's very cold, except it has an atmosphere. And so when photons reach the Earth is warmed, re-radiates to space. The atmosphere collects some of these photons and heats the Earth. So that's a simple picture. And here's a more complicated picture. The slides that I'm going to show are going to get more and more complicated. So you'll see the complexity of the problem. Basically, the balance of incoming visible radiation from the sun and outgoing infrared radiation from the Earth establishes the temperature. So when we talk about climate change, we're talking about how is this balance changing from whatever means, from the sun or from the trapping or whatever. So this figure here shows the sun coming in. It's not just the simple sun comes in, infrared radiation goes out. There are a whole lot of processes caused by the composition of the atmosphere, such as ozone, by clouds, the fact that the heat is also absorbed by land and ocean in different ways and radiated to space. Now, if that wasn't complicated enough, which it is, that's the radiative side of things. The incoming sunlight sort of tends to happen at low latitudes. And this is a picture here of the incoming sunlight. And incoming, then, the way that the incoming radiation is distributed with latitude, shown here, is peaks at the equator. But the outgoing heat happens all over the globe. And so the outgoing heat is less at the equator, but more at the pole. So this sets up a basic meridional differential in heat. And that causes the dynamical motions as a consequence. And so here is an example of that. The equator to pole thermal imbalance drives these circulation patterns that we are familiar with in the troposphere. So basically, you can think the heat has to get from the equator to the poles. How does it do that? It flows from low to high latitudes, and in the process establishes these circulation cells. And everyone's probably familiar with the Hadley cell, the polar cell, and the Farrell cells. And that then, the morphology of this dynamical pattern in the troposphere, initiated by the balance between the incoming and outgoing radiation, establishes dynamical motions that we're familiar with in weather, in terms of the trade winds shown here at the equator in the intertropical convergence zone, the polar jet, and the mid-latitude cyclone tracks. Now, this is important because the thermal gradient from the pole to the equator establishes things like the flow of the jet stream. And right now, we're having really hot periods in some areas because of a heat dome, and there's some sense that as the thermal gradient decreases, the polar jet becomes less and less stable and more wandering, having effects at lower latitudes. So you can see that this is a complicated system, and the sun is essentially the beginning of it all. But that's the troposphere. So now, if we think about our atmosphere where we live, above us is the ozone layer. And the ozone layer is important, of course, because it absorbs ultraviolet radiation from the sun, which is biologically damaging. So here I'm just showing most of the sun's radiation comes and reaches the Earth's surface. This is the visible radiation and infrared radiation and near ultraviolet radiation, but some ultraviolet radiation less than 315 nanometers is absorbed in the atmosphere, and it dissociates O2, which recombines with atomic oxygen and produces ozone. It also then destroys ozone at other wavelengths. So we have this balance of production and destruction by the sun, causing ozone, and this produces the ozone layer. So here I'm showing the ozone layer. I was talking in the previous slide about the troposphere, which is below about maybe 10 kilometers, this region of the atmosphere. We have the ozone layer, and it causes the temperature to increase. Now, the ozone layer has its own dynamical situation of patterns which sit above the troposphere. So this is like the circulation, the large-scale circulation of the atmosphere. Now, the sun is, if the sun changes, it changes the amount of ozone and changes this dynamical pattern as well. So you can see that we're talking about a really complicated system here. And as if that's not complicated enough, Brotherton and the Earth science community put together this figure that I want to sort of just present as the ultimate challenge of what we need to know to understand this whole system. I talked about the atmosphere, atmospheric physics, dynamics. I talked a little bit about the stratosphere. The sun is the external forcing of variability in all of these things, as are volcanoes. But all of these, the atmosphere and the stratosphere, all interact with each other. There are aspects related to the ocean, energy, moisture, and there are a whole lot of biogeochemical systems. The net effect is that Earth changes. It also changes because of a variety of increasing human activities, primarily the increase of fossil fuels, gases from fossil fuels, from various chemicals, and ozone depleting substances called chlorofluorocarbons. I'm going to talk about both chlorofluorocarbons and anthropogenic greenhouse gases. Now, when I talk about forcing by climate change, I'm going to use the net of the increasing greenhouse gases, which warm the planet, and the increasing aerosols by, for example, factory and auto emission, which actually cool the planet because they provide a layer over the troposphere that reflects radiation. So here we are. This is our system, and here is the sun. So how has this system changed? I mean, that is the really big question. So here is what we know. If I can get my thing to it. It's not working. I did. I think there's a bit of a lag here. Okay, so here's what we know. With a fair amount of confidence. From 1850, which is maybe considered to be the pre-industrial era, the global surface temperature, which is the temperature over this entire globe, has increased. And I'm showing you here 5 different records. So there's no doubt that this is happening. And the increases happen most recently in the last maybe 40 or 50 years. And the latest IPCC noted that the global surface temperature has now reached 1.1 degrees centigrade above the pre-industrial baseline. And people probably remember that, and I'm going to allude to this or come back to this, 1.5 degrees centigrade warming above the pre-industrial level has been this sort of golden lid where we don't want to bypass that in order to keep our climate more or less in the regime that we know it. Well, we're pretty close to it now, and I'm going to show you when I show you some predictions of the future. It's very likely that we're going to exceed it like pretty soon. You can see here from this map that shows the distribution of the warming, that it's not uniform. So the warming that we've seen is not uniform in either space or time. The stratosphere, on the other hand, so this is like just 20 kilometers above the surface, the temperature of the stratosphere has cooled. And I might add that in the past, over the past 40 years, there have been a number of people who say, well, the atmosphere is cooling in the stratosphere. Doesn't that mean that there's no global warming? No, it doesn't. And I'm going to explain to you why. And at the same time, ozone density is decreased. Now, there are different causes for these changes, and it's a whole mix of greenhouse gases, and in the case of ozone, chlorofluorocarbons. The interesting issue with ozone is that we put in place, or the politicians put in place the Montreal Protocol, which actually has now changed the amount of ozone destroying chemicals. So ozone is an interesting case because we're actually now not only waiting for it to decline or monitoring its decline or depletion, we're starting to ask the question, when will the ozone layer increase? In other words, when will we have an ozone layer that is free of anthropogenic gases? So now we would like to interpret these time series in terms of the various things that are causing them to change. And of course, the most obvious is the anthropogenic gases. As part of an earlier IPCC program, the various scientists put together what's called representative concentration pathways, which is the anthropogenic forcing in watts per meter squared that's occurred in the past and is projected to occur in the future. And you can see where we are now, the forcing is about 2 watts per meter squared. Now, 4 watts per meter squared is equivalent to what is called doubled CO2. Now, just as I said that the 1.5 degrees centigrade warming is a sort of benchmark. So in the climate models and in terms of understanding how the system will change is this concept of doubled CO2. That means when we've doubled the CO2 in the atmosphere. And you can see in this RCP 4.5 scenario, the forcing is somehow, magic happens, constrained to be at 4 watts per meter squared. And I'm going to show you some predictions using that. Oh, excuse me. Okay, in the bottom curve is the equivalent effective stratospheric chlorine. And the and this is the amount of chlorine that's destroying ozone. So going forward, I'm going to use this RCP4 scenario. It differs somewhat from a GIS scenario, but they both show a common increase. And I'm just showing you here that the greenhouse gases and the aerosols are both quite large. And then they compensate each other and form the net zero scenario. So we need to know also the solar forcing. And this is a very contentious issue because, let me go back here. We only have 40 years of observations of the total solar irradiance. And you might think 40 years is a long time, but in terms of climatological timescales, it isn't. But here we have a model, the NRL model of total solar irradiance. Sorry, I'm losing my voice here. And the variability components. As I said, the sun has a cycle, it has an 11-year cycle. And during that cycle, there are increases in the number of active regions on the sun's disk, including dark sunspots and bright faculae. These components compete with each other to alter the solar irradiance. And you can see there's a net increase in the irradiance at the peak of the solar cycle, which corresponds to net sunspot numbers. This is the total solar irradiance, but the spectrum also varies. And the green line here shows that the spectrum varies more at ultraviolet wavelengths than it does in the visible. So the solar spectrum itself depends on wavelength. The variability depends on wavelength, and so does the absorption in the atmosphere. Now, it's difficult to get from 40 years worth of measurements to a reconstruction in the past. And a number of people have tried to do this, and I'm showing these reconstructions here. And I want you to keep in mind that the solar cycle itself varies by about 1 watt per meter squared. Over the longer term, for the last 100 or so years, the speculations are maybe that there's a change in the background of order, like a little bit, maybe less than half a watt per meter squared. If you expand the reconstructions back in time, then you have, excuse me, scenarios like this from different models showing that there's a possibility that the sun's irradiance may have decreased by maybe a watt per meter squared. Now, this is not forcing, this is the irradiance in the past. And this is this blue reconstruction here, which is a recent one by Yiming Wang and myself, is what I'm going to use going forward when I try and show you past changes in climate and ozone and also future changes. Okay, so here is a summary of putting together the anthropogenic forcing, which is the RCP 4.5, and EESD stands for effective equivalent stratospheric chlorine. Here is the total solar irradiance with its 11-year cycle and possible longer-term changes. There are also volcanic aerosols that affect an external forcing of the climate. And this is a summary of the stratospheric volcanic aerosols. You can see El Chichon and Pinatubo here. Not much happening in the recent 20 years. This is important because I'm going to tell you about a period when, in fact, aerosols were claimed to have been causing climate change, but they weren't. And then the El Nino Southern Oscillation is a natural oscillation in the Pacific. Going forward, these are the 4 things that I'm going to use to predict future changes in ozone and surface temperature. I'm going to use a continuing 11-year cycle in irradiance, and I'll explain why when I get to the forcing. We don't know what volcanic aerosols will be, and this is a prediction of ENSO based on sinusoidal fits. So if we want to detect recent global change and understand the causes of it, then we can look at something like surface temperature. And this is an average of some of the surface temperature records that I showed you. The orange line is a model that's based on combining all these influences, including ENSO, volcanic aerosols, anthropogenic and solar influences. And you can see when you put those things together and determine their magnitude from regression, then you come up with a fit to explain the surface temperature record quite well. You can also do this at 5 kilometers. And this is the record at 5 kilometers. So these observations are made from space by the microwave sounding unit. They're completely independent of the record made on the surface. And you can see you can also produce quite a good reproduction of the ups and downs and the trends with these components. Moving up into the atmosphere, just 20 kilometers, the temperature of 20 kilometers, also made by the microwave sounding unit, has decreased, as I showed you earlier. These big spikes here are due to volcanic influences. There's a modest ENSO influence. There's a bigger solar influence because the sun now is, we're talking about the sun affecting the ozone layer. So this is the ultraviolet radiation that varies more than the visible radiation that reaches the surface. And one thing you can see here is that explaining the observed trend requires not just invoking anthropogenic greenhouse gases, which are causing the stratosphere to cool. And the reason that this is because the anthropogenic, the CO2, when it's in the troposphere, it radiates to space and the overlying atmosphere absorbs the radiation. But in the stratosphere, there's not much atmosphere above it, so it doesn't trap radiation. In fact, it radiates to space, and so greenhouse gases actually cool the stratosphere. This is the effective equivalent stratospheric chlorine, and the Montreal Protocol meant that it's now increasing. The temperature and also the ozone are both combinations of anthropogenic greenhouse gases and stratospheric chlorine. And you can see here the ozone, even though the ozone is existing at about the same region, 20 kilometers, it's the temperature, they actually have different structures because of the different influences. Now, the issue of greenhouse gases affecting ozone as well as chlorofluorocarbons is explained because the chlorofluorocarbons destroy ozone chemically. But the greenhouse gases cool the atmosphere above 20 kilometers, as I said, but they warm the surface, and this accelerates the Brewer-Dobson circulation, and there's an upflow of tropical air. So you can see that the issue of how these various anthropogenic gases interact is very complicated. It involves radiation, chemistry, and dynamics. Now, I showed you a reconstruction of climate using the period 1979 to 2022. We can check how well that reconstruction works by comparing with these 4 different surface temperature records going back in time. And you can see if you take those forcings, the solar forcing, the anthropogenic forcing, the ENSO and the volcanoes, and go back in time with the parameterizations derived from the recent data, you can actually reproduce the historical records, all of them, quite well. So this is a good test, an independent test, that this approach actually works quite well. You can't do that for ozone and temperature in the atmosphere because we don't have those records. But you can then, assuming that the fitting does okay in the contemporary period after 1975, you can actually then predict what ozone would have been in the past and the temperature in the lower stratosphere, in the middle stratosphere, and the troposphere. So what if, and this is like a bit provocative, but what if you don't know or understand that these are the things causing climate change? Well, we actually had a lesson of that from IPCC in AR5. They invoked, I want to explain a little bit about the consequences of not knowing, and I'm going to talk about this not only from a science perspective, but also from a political and media perspective. IPCC invoked a global warming hiatus, also known, quote, as the pause, to explain a lack of climate change from 1996 to 2014. So here is what they're talking about. 1996 to 2014, greenhouse gases kept increasing. So in terms of the public and the media, greenhouse gases are increasing, therefore we must have anthropogenic global warming. But we didn't have that in this period. And you can see here, 3 different records pretty much agree that over this period, there wasn't really a large upward warming. By the time you get to 5 kilometers, there was almost a cooling, and definitely at 20 kilometers, there was a cooling. So IPCC in 2013 says, it concluded the recent reduction in surface warming is probably due to, quote, redistribution of heat in the ocean, volcanic eruptions, and I'll get back to that because remember I showed you that there weren't really any in this time, and the recent minima in the 11-year cycle. The real reason that this happened is because the models that IPCC used, shown here in blue, basically predicted that there would be warming in this period, but the observations showed there weren't. The word out from IPCC was that these trends shouldn't undermine our confidence in the big picture of understanding climate change. In other words, IPCC said to everyone, trust us. Well, that actually provoked a massive amount of blowback from the media. And as I said, the part of the reason is because people at that time, which wasn't that long ago, 10 years, really equated anthropogenic global warming with global warming. So if greenhouse gases were increasing and the temperature wasn't, then, as this cartoon says, you know, warming, no warming over the last 16 years, et cetera, see, global warming. And then there's the message that IPCC gave, which is that scientists don't know why global surface temperature did not increase. And it's like, is global warming real? Of course, just ask the global warming theory. Now, this is sort of funny, and there are so many comic jokes like this, but it's really serious because this is our planet that we're talking about. And this implication of missing mechanisms exacerbated public and policymakers' lack of confidence in climate scientists and climate models with political and societal consequences. For example, there's been a hiatus in global warming, so let's pause the billion-dollar shift to green economies. The Earth science community jumped on this whole concept of the pause to do a whole lot of research, understanding what happened to the missing heat. So Martha Jones said, who created the global warming pause? Nature ran an article, the case of the missing heat. So these are the things that over the next few years, from 2013 up until maybe 2016, scientists published missing heat that had not warmed the planet was hiding in the oceans. The missing heat was then found in the Pacific. There was also the internal Pacific oscillation I talked about. Some people suggested that the cooling that didn't occur over this period were expected to occur was a result of industrial aerosols from China's coal. And this was a big thing for a while, like, oh, China's burning all this coal. This is, you know, so much that it's countering greenhouse gases, etc. There was invoked a background by volcanic aerosols, and I'll show you that this is basically not the case. There really weren't any that affected the climate. And then there was cooling from anomalously low solar irradiance or missing. Okay, so all of this. By 2014, the economist said, if all explanations were correct, the pause would now be explained twice over. There's an important line here I want you to notice, how climate skeptics and the media, okay, so it's true that a lot of the people promoting these, this idea that scientists don't really have an understanding of why climate is changing were climate skeptics in the media, but with a little inadvertent help from scientists themselves, i.e. the IPCC, set up this whole scenario that was actually very simple to explain. You can look at the period, I showed you the period from 1980 to in this case, 2018. This is the record that we're talking about. The period that everyone's talking about as, quote, the pause or the hiatus is this period here from about 10 years from 2000 to maybe 2011. And you can see that the model explains it really well. The global warming didn't stop because of anthropogenic gases decreasing. In fact, if you do the trends per this period here, the anthropogenic increase continued 0.15 degrees over this trend per year, over this per decade over this period. But what happened was the combination of a prolonged La Nina phase of ENSO. Remember, oops, sorry. ENSO is the El Nino Southern Oscillation. It has a period, a phase called El Nino, when like here is an El Nino that increases global surface temperatures, and La Nina, which decreases them. So over this period, we had cooler than average tropical temperatures in the tropical Pacific, aka hiding, and there was a decrease, a decrease from the maximum to the minimum of the solar cycle. And these are the numbers here. They all add up to the cooling by these three different natural processes countering the warming. So there really wasn't anything to fuss about. And you can see this also in the maps. These are the maps of the trends in the observations. This is the model. These are the observations. This is the model. You can see that the ENSO effect had cooling in the Pacific. So this was, heat hiding in the oceans. It was just a La Nina phase of ENSO. Minimal effect of volcanic aerosols. The solar irradiance cycle decreased, and there was cooling here at mid-latitudes. And the anthropogenic warming kept going. So there was no pause in anthropogenic warming. So why did IPCC's climate models predict excess global warming? To answer this, I'm comparing here the statistical model that I showed you earlier of the surface temperature observations, the model, and all the different components with a similar analysis, a statistical analysis of one of the physical climate models that IPCC uses, in this case, the Community Climate System Model 4. You can see that, for one thing, the models, this model in particular, overestimated the anthropogenic effect. And this is the longer time scale over the last 100 or so more years. It underestimates the solar irradiance. It overestimates volcanic aerosols. So all of it, and it doesn't have a reliable ENSO. This is particularly important because the models, the physical climate models, claim that they can do ENSO-like variability. In other words, they get some oscillations in the Pacific that more or less have the same period as ENSO does, like 2.6 years or so, but they don't get it in phase. So getting ENSO right was particularly important for understanding this cooling period here, but the models didn't forecast or didn't replicate our La Nina condition. So the reason I'm showing you this is I'm coming back to the sun in a way, because our reliance on climate models means that we really need to calibrate them some way. And I heard a really interesting talk by, I believe it was a climate scientist at the London School of Economics. And he said, you can think of the climate models as apples, right? So, and there are a lot of them. And generally, they're all apples. They all probably show the same thing. And in fact, I showed you IPCC's climate models all predicted warming over this period of the so-called hiatus. But maybe climate itself is an orange. The empirical statistical observation-based model that I'm showing here probably isn't an orange, but it's certainly not an apple. So the reason I'm showing you these things is by way of addressing how we might actually improve the models. And this is something that Steve Schneider talked about in 1977, a knowledge of the terrestrial climate variation due to the sun, which is this sort of external thing about which we presumably can know in detail its variability, could provide a gauge against which climate models can be calibrated. These models, in turn, are the only tools available for society to estimate the seriousness of the growing influences human activity may have on climate. So I'm introducing this concept of the sun as a calibration of climate models, which is a sort of slightly different view of what does the sun do and not do in terms of climate change. And here is the comparison of observation-based on the left versus theoretical models, in this case, the GISS model 3 on the right, estimates of solar activity changes in ozone, 20-kilometer temperature, tropospheric temperature, and surface temperature. You can see that the models get some aspects right, but they don't get some aspects right either. Now, the idea of this surface temperature map that I'm showing, you can ask, well, why do you even believe that? And in terms of the sun, we have a lot of paleoclimate records that exist before the industrial period, and against which we can actually, in a way, sort of calibrate this map of the surface temperature response that I showed you derived from comparing with modern observations. And there's an enormous amount of observational circumstantial evidence for these patterns being real. And these are just some of them here. And the gist of it is, and the fundamental aspect of it is that the response to the sun's changing radiation doesn't occur at low latitudes where the radiation itself reaches the Earth. But because of the dynamical patterns, it actually occurs at mid-latitudes, and that's a result of this transport. This is a very nice paper that actually spelled that out, and in terms of observations. And David Ryan had a really nice paper talking about the consequences in the model of the models not knowing low and high latitude climate sensitivity. In other words, if the models don't get the meridional flow right, then they won't be able to produce these climate patterns.
Judith, we have about 10 minutes left.
Okay, so good, thank you. So now I'm going to talk about the future, having explained, hopefully, the situation where we are now in terms of what we understand the past changes have been in terms of climate and ozone. We have to predict ENSO. This is really hard. This is a prediction recently, and you've probably heard in the media that we're expecting ENSO, let me rephrase that, an El Nino warming of the ENSO system should be happening about right now. We can't predict volcanic eruptions. I've shown you some scenarios of anthropogenic gases, and I'm going to show you projections with all of this. The sun is a difficult thing to forecast. We know it has an 11-year cycle. There was some talk about the sun going into a Maunder minimum, and that's because in 2009 and 2019, the minima in the solar cycle were as low as we've seen them in the past century. And so there was some talk about maybe a solar going into a Maunder minimum, in other words, a really low period of activity. The forecasts I'm going to show you have a continuing 11-year cycle plus an overlying 100-year cycle, and I'll explain why. Now, the whole idea of the sun going into a Maunder minimum has been a sort of let's see, how can I say? It's a wild card in terms of understanding future climate change, and solar physicists in particular particularly like to play this card. In 2011, at the American Astronomical Society, a solar physicist announced that the sun is fading. And if this is right, this is the last solar maximum we'll see for a few decades. Well, that's not right, because we actually now are in a solar maximum. But this provoked a whole lot of media response, including in the Washington Post, the Capital Weather Gang. And I know it's in this because Jason called me and interviewed me. And remember I said to you, think about the solar cycle corresponding to 1 watt per meter squared. This corresponds to about 1/10 of a degree centigrade change in global surface temperature. So going into a Maunder minimum would require that the sun cause a cooling of 1 degree centigrade, whereas it's more like 1/10 of a degree. This, nevertheless, stopped people saying that the sun was going to a Maunder minimum as recently as, this is only 3 years ago. A prediction from a solar physicist who runs a dynamo model, which is trying to understand how the mechanisms within the sun produce changes in the output. This person declared that the upcoming grand solar minimum would require intergovernment efforts to tackle problems with heat and flood. So basically, this is not going to happen, not on planet Earth, I don't think. But this didn't stop conservative media from saying, look, we don't have to act on climate change now because the sun is going into a Maunder minimum, and this gives us a good 35 to 50 years. This is not the case at all. So what I'm going to show you are projections of the future of the sun based on an 11-year cycle shown here, in which right now we're coming up to this cycle here, and possibly increasing cycle amplitudes in the future. From a solar physics point of view, the whole idea of the sun going into a Maunder minimum was not settled. And in fact, the people at NCAR predicted that, in fact, the new sunspot cycle could be one of the strongest on record. So you can see here, nobody really knows what the sun's doing. But in a paper that I have recently with Yiming Wang, we noticed that, in fact, there's a 100-year cycle in the amplitudes of the 11-year cycle. So the 2009 minima that everyone sort of thought was a precursor to a new Maunder minimum, when the sun's activity would just like basically stop, was actually the minima in 11-year cycle and the Gleisberg cycle. The Gleisberg cycle is something that has persisted for 10,000 years. Also, minima such as the Maunder minima and the Spora minima tend to happen in clusters of 2,400 years, and we've just had a cluster. So a Maunder minima type decrease is very unlikely in the near future, and if it did occur, I wouldn't cancel global warming. So when you see media commentary about this, please don't literally believe it, because I don't think it's true. Terry and I were talking about predictions before we started, and as I said, well, I'll be dead by the time these predictions happen. So I can happily go ahead and say that I expect the sun will keep cycling. The amplitude might even increase. So now I'm going to show predictions based on these 4 things, and just for reference, these are the 4 things that I've just used to explain the past. If we believe the RCP 4.5, in which the greenhouse gases were reduced such that we had a double CO2 warming, we will have a 2 degrees C global temperature warming. If we have business as usual, by the end of the century, we'll have 3 degrees C warming. And if there's something really extreme, which I doubt is going to happen, in other words, reducing the RCP scenario by 10%, that would keep the global surface temperature at 1 to 1.5 degrees centigrade. So these predictions are not at all dissimilar from what climate models say. And it's very likely that this is probably more serious. But as I said, one of the big issues is when will we reach 1.5 degree warming. Now, just for completeness, here are the ozone and atmosphere temperature trends into the future. This is business as usual, RCP 4.5, and then reduced RCP. You can see that the only way the ozone recovers is if we really reduce the greenhouse gases. And even then, by the end of the century, it's probably still not going to get back to the 1980 levels. Now, this depends, of course, on the model and the trends in ozone. We don't have a lot. So this is quite speculative. But you can see in the lower troposphere, the trends will typically follow the surface temperature. The whole issue of when will we reach 1.5 degree warming has just come up actually in the Guardian. Like this was like last month. There was a big article about when will we breach the 1.5 degrees climate threshold. Now you can notice that the media is talking not only about human-induced climate change, but about El Nino. So we've at least got the message across that an El Nino will warm the surface. And so here is the prediction of a coming El Nino. Yes, the temperature could warm, and this is like by 2024. What will probably happen, we will have an ENSO, but don't forget we're at the peak of the solar cycle now, and it's only a modest solar cycle. And so the temperatures might well stay there. So you can see what's happening here is just another case of the quote pause. We'll probably have another pause. We could well have another pause in the next decade, and people will then say, oh, but why isn't it warming? Anyway, so this is just a heads up of what might happen in the future. And if we actually do limit greenhouse gases so that they're flat, this is the greenhouse gases here, then the whole role of the sun in understanding everything is going to be much more pronounced, because we'll be trying to detect if the temperature is flat because we've reduced the greenhouse gases, but what if it's changing due to the solar cycle or ENSO? And this is true for the atmosphere as well. Now, I guess I'm not going to be able to finish all the slides that I have, but I do want to make you aware of the importance of decadal climate change. And there's now a UK Met Office effort started by Adam Scaife and Doug Smith that has recently become part of the World Meteorological Organization, where this model that I've shown you is part of it, but so are all these climate models. And the goal is to predict surface temperature distribution 1 year in advance for 10 years. So here are all the apples, the climate models. This is not an apple. This is an orange. In other words, these are the observations. So you can see on these timescales, there's a lot to improve in terms of the models. And I think understanding the sun is going to be part of that. Now, I'll skip through these last slides just to emphasize that everything I've talked about so far is looking at climate change in terms of linear combinations of greenhouse gases, solar forcing, ENSO, and volcanic aerosols. But we're now at the point where we can maybe expect feedbacks and tipping points. So one of those things is this cooling in the Atlantic. As greenhouse gases warm, the surface warms, it increases the precipitation here, decreases the strength of the Atlantic meridional overturning circulation, which is the ocean currents in the Atlantic, and you get a cooling here. And this is the basis of the day after tomorrow, Manhattan freezes. The climate models, the climate model that I showed you in terms of using the various different surface temperature records do show a cooling in the Atlantic, but not as much as here. So that's one tipping point or feedback that we may have to address in the future. Another is the whole issue of Arctic sea ice. And that's because the summer sea ice in the Arctic is melting and maybe will disappear in time. And because this changes the, remember I talked to you about the polar jet being dependent on the meridional gradient from the equator to the poles, changing the Arctic, more surface warming there, more reflection. This will then change the polar jet stream. And then finally, there's a whole issue of timescales. When we talk about a forcing, like solar, anthropogenic gases, etc., the net temperature that you get depends on the climate sensitivity. The climate sensitivity depends on all these feedbacks, including clouds, water, sea ice. And the feedbacks can take different times. So there's a big debate going on now where Jim Hansen says that the global warming that we've seen today in the pipeline that hasn't been realized is about 10 degrees centigrade. But then some people did some model calculations and they didn't find any zero commitment. So this is another region or another area where the sun can help, because if you put solar forcing into an energy balance model, which has only radiation and no dynamics, you don't even see an 11-year cycle. It's attenuated because the heat comes in and goes through the ocean and stays there. But the 11-year cycle is detectable in observations, and it's lagged by 3 months, not by years. And so this, again, may be where the sun and the response can tell us more about the feedbacks. Okay, so I'm finished. Summary. Solar radiation heats the surface and atmosphere, initiates dynamical patterns, transfers heat, creates the ozone layer. The sun is an active star of varies. It has an 11-year cycle, a 100-year Gleisberg cycle, and a longer-term cycle. So it's varying, and we can't stop that. So we have to understand it. We have to know how much it's varying and what it does do, but also what it doesn't do to the climate. Like as I explained, it doesn't. It's not going to. We're not going to have a mortar minimum, and it's not going to be able to cancel the global warming that we've seen. The climate and the ozone do respond to the changing solar radiation. They do. The variability is large enough to detect, but it's not so large to threaten habitability. So in this way, the whole concept of understanding the sun's influence on the Earth can be a calibration for climate model parameters. And going forward in the next, certainly the end of my lifetime, the reliable detection, attribution, and forecasting of anthropogenic influences will require a robust specification of solar influences, because it's a natural forcing that combines with other natural forcings. But also, if we're going to actually verify in the future the success of mitigation strategies, we need to know what the sun is doing. Okay, so sorry, that was over. I finished.
Wow, thank you so much.
Sorry about my coughing.
You did an amazing job, Judith.
I have allergies, sorry.
And I think it's very striking. You're giving a completely different perspective. I think for those of us who still think that temperature is proportional to forcing and that's all of it, it looks so much more complex. So good. So we have some time to go through questions. If you have questions, please write them down in the chat, and we'll try to answer them as many as possible in the 20 remaining minutes. First of all, we have a question by Steve Spangler. So Steve, can you please, can you speak? I turn on your mic.
Okay, can you hear me, Thierry?
Yes, fine.
Okay, thank you, Judith. That was a quite interesting tour de force, and I learned something, which is always a good indicator.
Sorry if I cough, it's because it means I don't know the answer to your question, but go ahead.
Well, I'm sure you do, actually. One of the things that struck me for years in looking at this famous profile plot of the average global temperature versus time, going back to 1880 to the present time, is it was an increase from about 1900 to 1940. This came to a peak, and then about after 1940, it plateaued to about 1970 when it started taking off with the current period. And that's always struck me as odd, because the Earth's population was a lot lower during that time. The energy used per person was a lot lower during that time. And I would have thought that the greenhouse gases would have been lower as well, although coal was a bigger contributor to the energy. So when I look at some of your models, it looks like they don't quite match that peak going back either. So I wondered whether, in other words, it looked like they undershot it a bit. So the question
are you talking about that peak around 1940?
Yes, I am. So the
you
question
know what happened then, by the way? That was World War II.
The beginning of World War II, but I don't think that's something that. So do you have comments on what that is, other than a possible statistical fluctuation?
No, I don't. I think it's no, I don't. But I can tell you that some people have suggested that it was fluctuations in the Atlantic meridional oscillation, and in fact, if you take an index of that, you can actually reproduce that peak. The problem with that approach of including that oscillation in the types of modeling that I'm doing, and I've proven this, is that it actually, the temperatures in the Atlantic actually lag the global surface temperature. And so it's a result of Phoemax not forcing. So no, I don't know.
Thank you.
Thank you for not knowing.
Okay, we move on with a question by Herb Veal. Okay, you have a long question, and it basically boils down to reconstructing glaciation periods. So I'll turn on. I'm trying to find your name. Here we are. Yes, you can. Normally, you can speak now. Herb, is it okay? Your mic is still muted. If you... Okay, maybe I'll read his question then. Is that...
okay, I think now we're
able... Okay, that will be easier.
Okay.
I'll let you go.
Okay, I'm wondering if the present models are able to reconstruct the former glaciation periods. Was that the sun, or, I mean, there probably were not enough.
I don't know. Oh, we do have a reconstruction going back to 850, but that's, you know, you would, I mean, okay, so. Okay, the long answer is, if you want to go back in time and know what the sun was doing, you need to use proxies like the cosmogenic isotopes in tree rings or ice cores. I didn't have time to explain this, but those proxies are due to variations in the open flux from the sun, whereas the irradiance is due to variations in the closed or total flux, and they're not the same. So I don't actually know how to get back to the past except by models that relate open flux and closed flux. And some people have tried to do that, but I don't know the answer. Sorry.
Okay. Well, thank you.
Sorry. You have to have another ISI seminar by someone who knows that.
Okay. So we have some comments, people commenting on each other. Valentina Zarkova is citing her paper. Tom Berger is commenting on Herb's comment. So next is Greg Cobb. So we have Mr. Kitai.
Greg asks me questions every day. He doesn't need to ask now.
I'm learning all the time, Judith, and I continue to learn more. Wonderful presentation, and thanks for that.
Sorry about the coughing. I knew that would happen anyway.
Gave me a chance to drink it, kind of to help empathetically. But what I was asking about was the 1.5 degree warming and how you think that should be presented. One thing would be, if it were a complete tipping point, the ice caps are going to melt, the meridional flows in the oceans are going to stop, and everything really is catastrophic once we hit that tipping point, then it's real serious. If it's been more of a goal that we should try for, we should present it a little bit softer, in that we don't want people to say, oh, we're going to hit 1.5 degree warming, it's all over, we may as well just give up now. How do you think that 1.5 degrees should be presented?
Okay, so I would defer to the view that Mike Mann, who is a famous climate scientist, has on this. And he's a professor at Penn State.
Oh, yeah. Yeah, I know.
He says that we have to be positive that we can do something. We can't say, oh, it's all over. The 1.5 degrees is something that people came up with because I don't know why. I think it was a metric to see if we could stay under it. And my friend David Ryan said he knew 10 years ago we were just going to blow by it. So I guess I would say the only thing we can do is keep
trying. Yeah.
The interesting thing with the 1.5, as I mentioned, was that at least now the media are saying, oh, there's going to be an El Nino. So at least they're getting that in. They still don't have the sun in. Ideally, to educate people properly about this, they would really need to have all the natural things involved. But really what you're asking about is you know, what's going to happen to the planet? Is it going to keep warming? And all I can say is yes, but I don't know.
Yeah, I'm asking about that, but also asking about how we should be presenting it. That is, we're not falling off the edge of a cliff, but we should still keep trying, I think, is
one thing I hope that everyone got from this is how climate scientists, people looking at climate variability, how tuned into everything the media is, and how it can get really distorted. So that it's really, I mean, the IPCC situation, like I wrote a paper on that, and originally the editor said, look, I can't publish this. This is a diatribe against IPCC. So I had to really soften it. But it struck me that we wasted all that time on this pause that didn't happen. So I think we've got to get the message out about what's happening realistically. And then that's the only way we can get the public to buy in and try and do something about this.
Yeah, yeah.
The sun, as you know, Greg, more than anyone, has been this wild card. Yes, the sun's doing everything. No, it's not doing anything. We've got to get the word out that the climate is changing and the ozone is changing for a whole lot of reasons.
Yeah. No. And thanks for the many years you've been doing exactly that.
Okay, so thank you. So next we have two climate scientists, and we start first with Adam Scaife. Adam?
Oh, Adam, I'm sorry I didn't have time to talk about your lovely decadal program.
Hello. Thanks, Judith. I really enjoyed your talk. It was great. And I very much like your linear regression models, even though I work with the comprehensive computer models. I think it's great that you do that work and that you keep
despite all the skepticism of that.
No, well, I mean, yeah, I think they're
fun. I really
they're really nice tools, actually.
Yeah, I think
yeah,
so.
And you probably know Chris Folland at the Met Office does some similar work.
Yes.
Draws some very similar conclusions. So I think they're great tools, and they keep everything grounded, and they're good to compare with. So I like that. And they're actually very good, as you've shown, for attribution and for understanding.
They're not as bad as you would think. There are a whole lot of issues about cross.
Oh, I don't think they are bad. No, I think you're right in many respects, and you made a lot of good points, including the conclusions from those models. I just wanted to
Thank you, Adam. Coming from you, that's a great compliment.
Okay, good. Yeah. I just wanted to see, though, if we could agree about the ENSO comment, because what I didn't agree with is the point you made about when you were talking about the hiatus. And I think you said something like models can't do ENSO or something. And I think that's a bit harsh. And the reason So, yeah, I suspect we will agree. I think
I've been beaten up on this before.
Yeah. So, I mean, you know, if you run a climate model, then you do actually often, in many cases, get very good simulations of ENSO variability and indeed the effect on the global temperature. The problem with the hiatus was that those long-range ENSO variations, they're not like the seasonal forecasts that we're doing at the moment for the coming winter, where we're very, very confident that a big El Nino is coming. They're talking about 10 years ahead, and there it's just simply not predictable. And so even if the model does do ENSO, you're not going to be able to predict the kind of detailed evolution through the hiatus period. So it sounds like you agree anyway. And so, I mean,
do agree. I do. Yeah. I do. But it's important to say that, right? Like,
yes, that's
why I tried to get the whole business about how the media saw this. You know,
I agree with that.
What I had to say was, look, we have a La Nina now. That's what I mean. Why didn't IPCC say this?
Yeah, I agree. We need to push harder on the IPCC to recognize the role of internal variability and natural variability in fluctuation of global temperature.
You know, like I've been around like long enough now to have experienced climate people, and in their defense, when all the whole issue of climate change started, the scientists had a hard time getting people to pay attention. So when someone came out and said, oh, it's just the sun, and there was, as you know, the whole, I think it was the Marshall Report that said, and all those people who were saying, oh, the sun's responsible. What? But so the climate scientists, and they've said this to me, no, the sun's not doing anything. So there's this, in order to make people aware of greenhouse gases and not the sun, it's almost like the climate scientists have gone overboard and said the sun's not doing anything. So now the sun is doing something, it's not doing a lot, but it is doing something on decadal timescale. So now we have to
Yeah,
re-educate people to say, well, yeah, the sun is there. It's like, it's not all or nothing.
Yeah, no, I agree. We shouldn't dichotomize. In human nature tends to dichotomize A or B. Obviously, both are important. And you've been very straightforward about the fact that the solar influence is much smaller than the anthropogenic. So I totally agree with you. Anyway, thanks a lot, Judith. A great talk.
Thanks for letting me be part of your decadal survey. I love that. I mean, whatever it is, decadal predictions.
Okay, well, Judith, there's someone else coming up. It's Jonah Haig. How about your regression models? Jonah?
Hi, Joanna.
Am I unmuted?
No, we can
No,
hear
we
you.
can hear you.
Okay,
I haven't seen
hi.
you for ages and ages.
No, well, I've sort of retired, but I hope you don't put me in the category of climate scientists who don't believe in a solar influence, because I've been working
you're
on
one
it
of the
for
first people
decades.
who did this.
Yeah. What I wanted to ask was, you're presenting your statistical model as sort of in competition with the GCMs and almost suggesting that it's better because it matches. But I think you need to put a backtrack on that a little bit. Firstly, because you're using the observations, so of course they match in a way. They have to. You're doing a best fit.
Yeah.
And the problem with that is, if you use those regressions into the future, you're assuming that the regression coefficients are unchanged. Now,
Absolutely, I totally agree with you. And I'm sorry if I was trying to say it's better. All I was trying to say is that it provides like an alternative thing, like it's not an apple.
No, but the climate models are actually trying to look at processes. They're really trying to understand what's going on. And just because they don't get it perfect all the time, doesn't mean that they're sort of somehow to be disregarded in comparison with statistical models, which are sort of cheating because they've got the results before you start.
Absolutely, and all that is a whole different layer of scientific investigation than what came out of IPCC. Look, I totally agree with you, and what I was trying to get at is that what would be fabulous if we could use both of them and say, well, the statistical model gives this pattern. Now, why doesn't the climate model give this pattern? Is it because they need to tune the meridional, equator to pole flow? Is it because they need to do this or that? I'm sort of saying what Steve Schneider said way back.
Okay, well, I won't prolong this argument.
I agree with you.
Climate models are tuning, they're tuning as little as they can, really. Anyway, there we are. Sorry. Nice to see you.
I'm used to push back on this, but I still think it's a fun thing to do.
Okay. So thank you, Joanna. We move on. We have a question by Valentina Zarkova. So I'm just trying to find where you are on the list. Ah, there you are. Sorry. Yeah, you can speak. Valentina?
I'm trying. Do you hear me?
Yes, fine.
Hi. It's a terrific talk, Judith. Thanks so much. And thanks for mentioning all the paper we actually
I know, it's like, of course, such a stir. I got emails from all over the paper. Oh my God, what?
No, we first predicted ground solar minimum in the Nature paper 2015, and at that time people did not believe it's going to happen. But now, many who have strong snows, you had this in America and Canada in December, and in Australia they had snow end of November, beginning of December. Their summer, they had snow. I had photographs. So what this ground solar minimum does, it doesn't reduce fully amplitude of the cycle. It reduces it slowly, and the most reduced amplitude will be cycle 26. So this is like beating effect, which happening. And what I wanted to ask you, why do you think it will not happen? Because it's already happening.
No, it's like cycle 26 will be another 15 years, right? The maximum of cycle 26.
Yeah,
because we're in cycle 25 now.
Mm-hmm.
Right.
Yeah, but even on cycle 25 descent, we will see the signs, much more signs of ground solar minimum, because we done another work on volcanic eruptions, paper recently published. I provided the website which you can download the papers from there. And it is strong relationship. In cycle 26, we will have huge amount of volcanic eruptions. And this
I'm actually expecting that solar cycle 26 will be higher than solar cycle 25 because of the impending Gleisberg cycle. And so you say it's going to be lower. So we should have a bet on this. And then 10 years later.
We predicted from real data, from real magnetic data. So it's not like a bet. What I'm saying that I understand you have your beliefs, and the Gleisberg cycle is pretty important. It's fine. But what is happening, we cannot deny that the temperature now been decreased. I don't know how it is in the United States, but in the United Kingdom, we had heating running until end of May. It was very cold here. So this is
Can I comment on that? I think what you're talking about and what's happening here is the dynamical response of the things like the polar jet to the increased greenhouse gases that are warming the Arctic, because as I showed, when there's a more shallow difference between the equator and the poles, and the polar jet wobbles around, and that allows hot air to stay in place longer, and it allows colder air to come down more often. So the idea of the snow coming down to mid-latitudes, that I believe is related to the wobbling of the polar jet. It's not.
Yes,
related.
it is, exactly, because the ozone level is decreased because less UV radiation. Absolutely agree. I remember Shadow et al. 2001, this beautiful paper. They explain how this is acting. So about ground solar minimum, we will see within next 5 years. It will be as we predicted, believe me. You can believe anything you like. But it will be
the next solar minimum, which will be, I suppose, 2030. We'll be able to look at the polar fields and see the strength of the polar fields, and that will actually, like say, give us a clue as to whether the next solar cycle 26 will be higher or lower. Okay, so
let's be in touch. Let's be in touch. I'm very happy to be in touch about it because I like to persuade people with the facts. Another question is about your global warming, which you have, and you did mention it, but we also published paper, and I recently published book chapter showing that the solar inertial motion, when the sun shifts from the focus of the ellipse towards closer to the orbit, causing very strong heating. And this heating probably hits the ocean. I've seen the people who do climate model, they say they don't know why the ocean is heated so much recently, but it is heated during the February until July because sun is closer to the Earth orbit and the position of the spring equinox. So this gives you, and this change happens every 2,000 years. Holstad cycle, basically it is the motion of this solar inertial motion. So if your models could include this additional extra heating into, then it would be possibly much better coherence with observations, because we downloaded the temperature and compared with the variation of solar magnetic field, and we found very strong correlation of the Earth temperature with the variation of solar magnetic field. Paper now under the preparation, we will submit soon, but believe me, you are very close to discover much more strong heating.
No, I heard an interesting, this is not my idea, but I heard it from someone, and it was a really good idea, which is that the current understanding of the amount that the sun changes and the amount that the greenhouse gases changes are giving us a good representation of the global surface temperature warming in the last 150 years. So if you say that the sun is doing more, then that means you have to say the greenhouse gases are doing less. And that's different than the absolute basic simple theory, like the greenhouse gases are increasing. We have measurements of that. So you would have to postulate this, not only an increase in the sun beyond what we've seen, but a decrease in the response of the greenhouse gases, so that the odds are stacking up against the sun doing more than I've showed, I believe.
Mm.
But that's the fun of predictions.
I'm very happy to discuss with you over email. I'm delighted with your work. We're citing your early work. So I really appreciate what you do and happy to discuss and persuade you at some stage.
Okay,
You can.
but I bet we're not going to have a 1 degree warming.
So-
I bet.
Yeah, thank you.
So
Cheers.
Okay, thank you.
I think we'll probably stop here. I think my conclusion from that is that we meet again in 15 years from now to see who was right. And Judith, I'd like to thank you again for this. I think this was an awesome talk. And I think that you made a point on a very important thing, is that it's not just about looking for correlations, but it's really about understanding the physical mechanisms. And from that perspective, I think your talk was really outstanding. So thank you so much again. For all of those of you who are listening, you can still listen to the talk online. It will be on the EC website. And hopefully we meet you again next month for another webinar. So thank you all very much, and hopefully see you soon again. And thank you, Judith.
Thank you, Terry. Bye-bye, everyone.